The first part of this video is dedicated to making a stock solution, for example, a substrate solution for an enzyme activity assay. Here we choose dopamine. Amines clearly has an amine group and then a catechol group as well, so it's a catechol amine. You already looked up dopamine in another assignment. Dopamine is commercially available in the hydrochloride form. It's much more soluble in its hydrochloride form and more stable. There are many alternative names, and you can test your knowledge of organic chemistry. Let's look at the calculations on how to make a stock solution. First, make sure you have the correct molecular weight, the one for the dopamine hydrochloric acid. Then in a lab notebook, you would write out all the details of your calculation with proper units. The formula is volume times concentration times molecular mass. Don't forget to record the actual weight that was used. Now some comments on lab technique. There are two alternatives on how to prepare a stock solution, but in both cases you need a volumetric flask. And for a stock solution where concentration really matters, you need to use an analytical scale. To deliver tiny amounts, I'm tapping my wrist with the other hand. In this first preparation method, I'm dissolving the solid dopamine hydrochloride in distilled water, and then I'm transferring into the volumetric flask. This method is useful if you're not sure how soluble your compound is and you really want to stir with a magnetic stirrer. Then you have an additional beaker, so you need to rinse a few times through the beaker. So here I'm showing you the meniscus of the volumetric flask to get the volume as accurate as possible. The next alternative is to transfer the solid powder directly into a volumetric flask. In this example, it's a smaller volumetric flask, but then all the mixing needs to happen inside the volumetric flask. There is less glassware involved, so more quantitative transfer, but it's less convenient to dissolve the powder, and it's more difficult to get the powder into the narrow neck of the volumetric flask instead of the beaker. Next, we look at biochemical buffers. Biochemical buffers consist of a weak acid and its conjugated base, or alternatively, the weak base and its conjugated acid. The weak base can take care of extra protons and the weak acid of hydroxide ions, thereby stabilizing the pH. The Henderson-Hasselbalch equation can be used to calculate the pH of a buffer solution if you know the pKa of the weak acid and the concentrations of the conjugated acid-base pair. Phosphate buffers are very typical for a biochemistry lab. When you prepare a phosphate or any other buffer that comes as a salt, pay close attention to the form it's delivered. So whether you get anhydrous salt or a salt with several water attached. To make a stock solution for a buffer preparation, it is typically sufficient to use a top loading scale. To dissolve the solid component, use a large beaker that's better to stir than a narrow cylinder. And don't use all the water at once, leave some room to fill up to the final volume. Here is an example on how to avoid the retrieval of a stir bar. Just hold your glass container with a large stir bar. Next, we look at buffer calculations. The most important equation for buffers is always the Henderson-Hasselbalch equation, but don't forget that a final buffer concentration is made up of the conjugated acid and the conjugated base. If you have two unknowns, the concentration of A-, the conjugated base, and the concentration of the weak acid, you always need two equations to solve for two unknowns. So these two equations will be used in the following exercise. You're asked to make a buffer calculation. You'll find a very similar problem on Blackboard, all worked out. So you can stop the video, check out the Blackboard document on the detailed explanations on how to do a buffer calculation, and then answer the final quiz questions of this unit.